What connects a screaming Detroit two-stroke, a silent marine engine that refuses to start, and a ship's power plant rising 3 stories above its crew? Across workshops, test cells, tugboats, tankers, and heavy machines, diesel power survives through noise, pressure, diagnosis, maintenance, and scale. This journey follows forgotten engines back to life, then enters the mechanical worlds that move industry across land and sea today. The journey begins with an engine whose voice belongs to another industrial age, the Detroit Diesel 453T. It is part of the Series 53 family, built around a compact but unmistakable 2-stroke design. 4 cylinders stand in line, each displacing 53 cubic inches, giving the engine a total capacity of roughly 3.5 litres, or 112 cubic inches. The final letter in its name, T, identifies the turbocharger, feeding additional air into the cylinders. Unlike a quiet modern power unit, this engine announces every combustion event. Its rapid firing unit, high operating speed, and sharp mechanical roar made Detroit two-strokes instantly recognizable on work sites and roads. Engines of this family served in trucks, construction equipment, and military machines, where durability mattered more than refinement. That compact roar now leads us into a diesel system built like a cathedral. Aboard the commercial tanker Iver Expert, diesel power is no longer contained in one compact block. It becomes an entire vertical landscape of machinery, pipes, platforms, tanks, and service systems. At the center stands the MAN BMW 6S50MCC main engine, a 6-cylinder, 2-stroke marine diesel designed for the continuous demands of a large cargo vessel. Each cylinder has a bore of 50 centimeters, and the long-stroke arrangement is intended to produce efficient propulsion and strong cooling power at sea. The tour begins high above the crankshaft on the cylinder head deck. From this level, the 6 cylinders appear as individual power stations joined into one engine. The cylinder covers seal the combustion spaces, while the exhaust valves control the release of burned gases after each power stroke. High-pressure fuel pipes run toward the injection equipment, delivering fuel at the moment required for combustion. Every connection must remain secure because the engine works under sustained pressure, heat, and vibration. Moving downward changes the scale of the machine. What looked like separate components from above becomes a single structure extending through multiple working levels. The middle platforms provide access for inspection, adjustment, and maintenance. Below them lies the lower engine area, where the mechanical forces generated in the cylinders are transferred toward the crankshaft and ultimately to the propulsion system. The engine room is arranged so engineers can reach critical machinery without stopping the vessel's entire operation unnecessarily. Yet the main engine cannot operate alone. Around it, Auxiliary engines and generators supply the electricity needed throughout the ship. Lighting, controls, pumps, ventilation, accommodation equipment and other onboard services depend on this electrical power. Even when the main engine is devoted to propulsion, the generators maintain the ship as a functioning workplace and living environment. Fuel preparation is another continuous task. The vessel may carry fuel oil or diesel oil, but neither should be sent directly into important machinery without treatment. Purifiers and separators remove unwanted material from fuel before it reaches the engine. Similar equipment cleans lubricating oil, helping protect bearings and moving surfaces from contamination. These machines may appear smaller than the main engine, but their work directly affects reliability. A giant diesel can be damaged by particles that are almost invisible. Pumps form the circulation network of the entire engine room. Seawater pumps move external water through cooling systems. Freshwater pumps circulate treated water through internal cooling circuits. Lubricating oil pumps maintain the film that separates heavily loaded metal surfaces. Ballast pumps move water between tanks to help control the vessel's balance and operating condition. Each pump serves a different circuit, yet all of them support the same objective, keeping temperatures, pressures, and stability within safe limits. The auxiliary boiler adds another layer to this mechanical ecosystem. It produces steam used to heat heavy fuel oil, allowing the fuel to flow and be handled correctly. Steam also supports domestic services aboard the vessel. This means the engine room is not merely a propulsion compartment. It is a combined power station, heating plant, pumping station, fuel treatment facility, and maintenance space. Walking through these levels reveals why large marine diesels can run for long passages. Their size is only one part of the answer. Reliability comes from redundancy, preparation, monitoring, and constant circulation. Fuel must be clean, oil must be purified, cooling water must continue moving. Electrical power must remain available. Steam must be produced when needed, and ballast must be managed as the ship's condition changes. The crew, therefore, does not simply start the engine and leave it running. Engineers watch the network surrounding it. A change in pressure, temperature, flow, or electrical demand can point toward a developing problem before it becomes a failure. Access platforms, valves, pipes, gauges, and service equipment make this supervision possible. From the cylinder head deck to the bottom of the engine room, the IVA expert demonstrates the true scale of marine diesel engineering. The six-cylinder main engine supplies propulsion, but dozens of supporting machines make that propulsion dependable. The vessel moves because an organized system continuously cleans, cools, lubricates, generates, pumps, heats, and balances. What began with the uncontrolled scream of a small Detroit engine has now become the opposite. Enormous power controlled through layers of disciplined machinery. The deeper the tour goes, the clearer this relationship becomes. No single machine carries the ship by itself. Propulsion depends on a chain of smaller processes, each operating before, during, and after combustion. Together, they turn the engine room into a managed industrial organism beneath the tanker's working decks. From continuous propulsion, the story turns to power that must arrive instantly. Emergency power is measured not only by output, but by response time. The MTU on-site energy generator set, driven by a 20V Series 4000 engine, faces an NFPA 110 Type 10 load acceptance test. After starting, the unit must take its full load of 3,250 kilowatts within 10 seconds. It reaches 100% in 9. Voltage and frequency dip when the load is applied, then recover within seconds, settling to deviations of only a few tenths of a percent. Here, reliability means power delivered before critical systems can be interrupted. But instant power means nothing when an engine refuses the first revolution. The next marine diesel presents a very different challenge. A MAN 800 will not start, so the investigation begins with the simplest conditions that can prevent combustion. Technicians first inspect the fuel supply system, including filters and the fuel feed and return valves. They also confirm the ZF control is in neutral, because the starting circuit will not permit engine operation when a gear is engaged. These basic checks do not reveal the fault. When the ignition is switched on and the starter is pressed, the fuel stop solenoid remains in the shut-off position. Instead of releasing towards the fuel delivery position, it continues commanding zero fuel. The starter can turn the engine, but without fuel, the cylinders cannot begin producing power. The same behaviour appears on both engines. That detail changes the direction of the diagnosis. Two independent mechanical failures at exactly the same time are less likely than one shared safety interlock holding both engines in shutdown. The technicians therefore look beyond the individual engines and examine the systems that can issue a common emergency stop command. Attention turns to the Fireboy automatic fire suppression system in the engine compartment. Its pressure switch is tested first. The reading is approximately 0.3 ohms, indicating that the circuit is closed and the pressure switch itself is operating normally. The problem must be farther along the shutdown circuit. The team then checks the Fireboy relay box. Inside, damaged or sticking relay contacts are keeping the circuit in an emergency stop state, even though no fire has occurred. Because the relay box falsely signals a hazardous condition, the stop solenoids remain activated and prevent both engines from receiving fuel. This repair story shows why diesel troubleshooting must follow evidence rather than assumptions. Fuel filters, valves, control position, solenoids, interlocks, pressure switches, and relays form one starting chain. A failure far from the engine block can make healthy machinery appear completely dead. By tracing the shared signal step by step, the technicians locate the real fault. Not a failed diesel, but a safety system that refuses to release it. Once the false shutdown is removed, fuel control can return. With the fault isolated, a smaller marine diesel can finally breathe. The Yanmar 6LY2A STP offers a demonstration of a used marine engine returning to work. This inline six-cylinder diesel is rated at 440 horsepower and is started from the Yanmar control panel. As it begins running, the instruments show oil pressure building and temperature stabilizing, two signs that lubrication and cooling are functioning. External water circulates through the cooling arrangement and is discharged through the exhaust outlet, making the flow visible during the test. The operator then increases engine speed to examine throttle response. The diesel climbs through the revolutions cleanly, without hesitation, restriction, or abnormal black smoke. The control panel hour meter shows approximately 620 operating hours. That number alone cannot describe an engine's condition, but the demonstration provides evidence of how this unit starts, circulates cooling water, develops oil pressure, reaches temperature, and responds under speed. After the Silent Man investigation, the Yanmar reminds us what starting looks like: fuel, air, lubrication, cooling, and control working together from the command. That compact test now expands into machinery towering through 3 shipboard levels. Inside the Ro-Ro cargo ship, the main engine rises through the engine room like a building. It is a slow-speed, 6-cylinder, 2-stroke diesel standing roughly 3 stories high. Its purpose is direct and uncompromising. Turn the propeller shaft without an intermediate reduction gearbox. At maximum operation, the shaft rotates at about 100 revolutions per minute, slow by road engine standards, but appropriate for moving a large vessel efficiently through the water. Direct drive also changes how the ship reverses. The propeller does not depend on a conventional reversing transmission. To move astern, the main engine itself is started in the opposite direction. The sequence must therefore control the engine's stopping position, starting air, fuel delivery, and timing so the crankshaft begins rotating backwards. A machine of enormous mass becomes reversible through carefully ordered commands. The tour exposes the systems that allow this process to happen. Along one level are the 6 cylinder heads, each covering a combustion chamber, large enough to make ordinary vehicle engines seem miniature. Fuel injection pipes deliver fuel to each cylinder, while hydraulic lines control the exhaust valves. The arrangement shows how separate cylinders are coordinated as one propulsion unit. Below and beside the cylinder level runs the scavenging air system. The scavenger air trunk performs a role similar to an intake manifold, but on a vastly larger scale. Fresh pressurized air enters the cylinders after combustion gases leave, clearing the cylinder and preparing it for the next cycle. Because this is a 2-stroke engine, effective scavenging is essential every revolution. Two large turbochargers supply that pressurized air. Exhaust energy drives their turbines, and the compressors force more air toward the engine. Compression raises air temperature, so the charge air cooler removes heat before the air reaches the cylinders. Cooler Denser air supports efficient combustion and helps keep thermal conditions under control. Lubricating oil also gathers heat while protecting bearings and moving surfaces. A plate cooler transfers that heat away from the oil circuit. Pumps keep the oil moving, maintaining pressure and flow throughout the engine. Without that circulation, the metal surfaces carrying the engine's immense loads would lose their protective film. Crankcase inspection doors provide access to the engine's lower internal spaces. Through these openings, engineers can inspect conditions around the crankshaft and related components when the engine is safely stopped. The doors represent an important feature of large machinery. Every hidden region must eventually become reachable for examination and maintenance. Starting this engine requires another system entirely. Large start air bottles store compressed air. When a start command is given, that air is admitted directly into the cylinders in the correct sequence. The pressure pushes the pistons and begins turning the crankshaft before normal fuel combustion takes over. The stored air must contain enough energy to overcome the resistance of the stationary engine and establish rotation. Together, the start air bottles, cylinder equipment, hydraulic controls, turbochargers, scavenger trunk, coolers, pumps, and crankcase access points reveal the engine as a network rather than a single object. Each part serves a stage in the cycle: starting, breathing, injecting, burning, exhausting, cooling, lubricating, transmitting force, and preparing for inspection. The Ro-Ro engine room also demonstrates the difference between visible speed and useful power. The propeller shaft may turn only 100 times per minute, yet every revolution delivers a massive impulse through the water. The engine does not need the high rotational speed of the earlier Detroit diesel. Its scale, cylinder dimensions, and direct connection to the propeller allow low-speed operation to become an advantage. From the upper cylinder heads to the lower crankcase, the machine is designed around sustained propulsion. It can start forward, stop, restart backward, and continue driving a ship loaded with vehicles and cargo. What sounds simple from the bridge depends on compressed air, controlled fuel, cooled intake charge, circulating oil, and synchronized exhaust valves deep below. Here, diesel power has grown from a workshop engine into architecture. After this towering architecture, attention returns to a compact, carefully preserved unit. The 2006 Volvo Penta D6350AB represents another side of diesel history. An engine preserved not as a museum object, but as a complete working package ready for continued marine service. Rated at 350 horsepower, the unit is presented in clean, original, and well-maintained condition, with only 581 operating hours shown.
To go onto a Volvo Penta DPH.
Its cooling arrangement is fully based on seawater service and includes a heat exchanger. Rather than allowing engine temperatures to rise unchecked, the system transfers heat away while keeping the diesel within its intended operating range. A high-grade stainless steel exhaust assembly completes the marine installation, where resistance to water, heat, and corrosive conditions is essential.
So we'll fire her up.
The equipment supplied with the engine is equally important. A complete Volvo Penta EVC instrumentation set is included, allowing the operator to monitor and control the engine through its matched electronic system. Additional gauges are shown stored in their box for the buyer, preserving the supporting components that make installation and operation more complete. The engine is configured for a Volvo Penta DPH stern drive system, including the required drive equipment. That configuration links the diesel's output to a propulsion arrangement designed for maneuverable marine use. Compared with the towering slow-speed engine inside the Ro-Ro vessel, the Volvo is compact and self-contained. Yet the same principles remain visible. Cooling, exhaust handling, monitoring, control, and transmission must all match. Preserving an engine therefore means preserving the system around it, not merely keeping the block clean. Only then can stored machinery become dependable propulsion, again on the water. One preserved engine leads onward to a tug built around total redundancy. The ALP Defender expands the story from one engine to an entire offshore working vessel. The tour begins at two bow thrusters, machines that help the tug turn, position, and maneuver in confined water. During towing or rescue work, this control can be as important as forward power because the vessel must respond while handling heavy external forces. Farther inside, the engine room reveals the main engines and their transmission systems. These provide the power needed for demanding ocean operations, but they are surrounded by equipment that keeps the ship independent during long voyages. Generator systems produce electricity for machinery and living spaces. Waste treatment equipment manages onboard services, while a freshwater plant converts seawater into usable water. Refrigeration, ventilation, and air conditioning systems control the internal environment. Their purpose is not secondary comfort alone. Machinery spaces require airflow and temperature management. Stored supplies need suitable conditions, and the crew must remain able to work and rest throughout operations. Approximately 35 people can depend on these systems at sea. For them, the engine room supports propulsion, steering assistance, electrical power, water production, waste handling, cooling, ventilation, and daily life. The ALP Defender is therefore not simply a tug with powerful engines. It is a self-contained platform prepared to operate far from shore. As the tour passes through each compartment, the vessel's complexity becomes clear. Giant diesel power makes towing possible, but survival and control come from the network around it. Every auxiliary machine extends the tug's endurance and keeps its crew effective. From ocean endurance, the journey returns ashore to machinery opened for renewal. Back in the workshop, a Caterpillar D4H Bulldozer stands midway through an engine rebuild. Parts of the engine installation and surrounding bodywork have been removed, exposing the machine for repair. The scene captures a stage between failure and return. The machine is incomplete, but its structure remains ready to be restored. A smooth walk-around shows the bulldozer from every side. The blade dominates the front, while the tracks, sprockets, supporting chain, protective cab frame, and open engine compartment reveal how propulsion, traction, infrastructure and operator protection combine in one machine. The video also tests a DJI gimbal. As the camera operator walks around the workshop, stabilization keeps the movement controlled and the details readable. That steady view matters because rebuilding requires close observation. Missing panels, exposed components, wear plates, and mechanical connections become easier to examine. Unlike the ship engines, this diesel is silent and partly dismantled. Yet its condition does not mark the end. Rebuilding turns forgotten or worn machinery into useful equipment again, one component at a time. The final start brings this history forward into modern common rail power. The MAN D2-676 closes the journey with an interpretation of the inline six-cylinder diesel. Built by MAN Truck and Bus, this common rail engine uses a 4-stroke cycle and liquid cooling. Its fuel system represents controlled precision that earlier machines pursued through mechanical arrangements. When the engine starts, the sound is unmistakably diesel, but the application has changed. The D2676 serves heavy MAN TGX and TGS trucks, long-distance buses, construction machinery, and industrial equipment. One engine family can therefore support transport, infrastructure, and stationary work across different environments. From the screaming Detroit two-stroke to marine engines rising through multiple decks, every machine depends on the same discipline. Air, fuel, cooling, lubrication, starting control, and maintenance determine whether forgotten iron remains silent or returns as dependable power.